Okay, so what we are going to do now is the phosphate anion. So let's draw the phosphate anion. So phosphate is PO4 3 minus. We'll learn the names of these things a little bit later, but for now let's just learn how to draw them. So phosphorus is group 15, so it has 5 valence electrons. Oxygen is group 16, so it has 6. And again, there are 4 of them, so that is a total of 24 that we have to deal with. And then this is a 3 minus anion, so there's an additional 3 electrons that we have to account for. So 4 and 6 is 24. 24 and 5 is 29. 29 and 3 is 32. So we have 32 valence electrons to draw in our picture. So I'm going to start it over here. Here's phosphorus, and we're going to draw single bonds. That's 8 of my 32 electrons. So 32 minus 8, we have 26 electrons. 24 electrons left to play with. So then I'm going to put my oxygen atoms in. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, subtract 24, and 0. So if we'll look at this, notice everything has a perfectly good octet. Each oxygen has 8 atoms, the phosphorus, 8 electrons, and the phosphorus also has 8 electrons. So this is, in fact, a good resonance structure for the anion phosphate, which has a total 3 minus charge. Okay, now I'm going to clear off a little bit of stuff here because we're going to need the space. All right, so the first thing that I'm going to note is that this is a perfectly good Lewis structure, and we can assign things like shapes to this. Notice that there are no lone pairs on the central atom, so we have a central atom with 4 external atoms and no lone pairs, so we can either just call it AX4, or to be very clear, we could call it AX4E0. The steric number are these two numbers added together, so this is steric number is going to be equal to 4. This thing has a shape that is tetrahedral. And we can draw that out by saying that we have a phosphorus going up to an oxygen atom, going down to an oxygen atom, coming out towards us to an oxygen atom, and going away from us to an oxygen atom. Okay, and that this whole thing here has a 3 minus charge. So this is kind of standard for determining using the Lewis structure to interpret it, to get the shape. Now let's just go ahead and assign formal charges. So again, what do? We take the number of valence electrons and subtract the number of things touching it. So oxygen is supposed to have 6. It's got 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 means this oxygen has a negative formal charge. In fact, all of the oxygens here have a negative formal charge. What about phosphorus? Phosphorus is supposed to have 5, and it has 1, 2, 3, 4. So 5 minus 4. So phosphorus actually has a positive formal charge. Now this is not good, because notice that we don't have any zeros in our picture. And typically zeros are better. So we should ask ourselves, is there a better way to draw this? And the answer is yes. We can draw, in fact, a resonance form. And the resonance form will look something like this. If we take and make and turn 2 of these electrons into a double bond, instead of having, we would typically show this by saying that this lone pair moves in. This is called arrow pushing. And we take this lone pair on the oxygen and turn it into a bonding pair instead of a lone pair. So there are still 2 lone pairs on this oxygen. But now we've made one a bonding pair with the phosphorus. And let's just recopy everything else. Okay, so what's going on with this picture? First of all, it's still a 3 minus ion. All we've done is change where the electrons are located in our picture. Same number of electrons, everything's the exact same. The only difference is phosphorus now has 10, and that's called an expanded valence shell. And this is perfectly good for phosphorus. It's not something that we could do for oxygen because oxygen is a period 2 element. But for the period 3 elements, the third row of the periodic table and down, things like sulfur and phosphorus and chlorine and so forth, these are perfectly fine with having more than 8 electrons in an expanded shell. So if we count the formal charges here, we're still going to get minuses for these oxygen atoms. But now phosphorus is supposed to have 5. It has 1, 2, 3, 4, 5. That's a 0 for the phosphorus. Oxygen is supposed to have 6. It has 1, 2, 3, 4, 5, 6. That's a 0 for this top oxygen. And this is a better resonance form. Why? Because this one has all atoms with formal charges. This one has only 3 atoms with formal charges. So we can continue to do this and basically now just walk the double bond around. I'm not going to draw all these, but you'll get the basic idea. We can draw the same picture except with the double bond in a different location. All of the single bonded oxygen atoms are going to have 3 lone pairs, and the double bonded oxygen atom will only have 2 lone pairs. So let's show that. And now this one has a negative formal charge, this one has a negative formal charge, and this one has a negative formal charge. Notice our formal charges have to add up to give us the overall charge of the ion, which is negative 3. So there's going to be 3 minuses. And we could continue to do this. So I'm just going to put this as an etc. So just moving that double bond around. So our resonance hybrid is going to look something like one of these 3 best Lewis formulas. It will be somewhere between a single bond and a double bond, and all of these bonds will be equivalent. There's one more, so we could draw the hybrid. So I'll draw that here. So here's the hybrid. And what is the hybrid going to look like? It's going to be a phosphorus. It is going to have 4 oxygen atoms, but none of them are single bonds and none of them are double bonds. They're all somewhere in between. Okay. Now you might say, well, if we made 1 double bond and expanded the shell and that made a good Lewis formula, why don't we make 2? So let's expand by putting a second lone pair in and see what that does. So here we have phosphorus double bonded to oxygen, double bonded to this oxygen, single bonded here, and single bonded here. So let's see what that gives us. So again, the ones with double bonds are going to have 2 lone pairs. That gives an octet. And the ones with single bonds are going to have 3 lone pairs. That looks like 2 electrons. That gives an octet for each of these. And phosphorus has an expanded valence shell, but we just said that that's okay. So is this a good Lewis structure as well? Well, let's ask the formal charges. So if we look here, the formal charge of this oxygen is negative. The formal charge of this oxygen is negative. What about phosphorus? Phosphorus is supposed to have 5. It now has 1, 2, 3, 4, 5, 6. 5 minus 6 is negative. So notice what's happened. We still have our 3 negative formal charges, but now they are on atoms that are actually connected to each other. Oxygen is connected to phosphorus, and phosphorus is connected to this oxygen, and they all have the same negative charge. This is called negative charge on adjacent atoms. Let me draw it up here so you can see it a little better. Phosphorus and oxygen, This one has a negative charge, and this one has a negative charge. These negative charges don't like each other. They repel. That's not the same thing as here. Here I have a negative charge, and a negative charge, and a 0 on the phosphorus. So the phosphorus acts as kind of a buffer. Okay? And so this one is considered to be a poor Lewis formula. It's not wrong. It still has the right number of electrons. It follows all the rules correctly, but we do not consider it to be a contributor to the resonance hybrid. It is not what the resonance hybrid looks like because it has this incorrect picture putting these negative charges on adjacent atoms. We'll also learn when we talk about electronegativity that when you do have negative charges, you want them to be on the most electronegative element, which in this case is oxygen. So in these pictures up here, all the negative charges are on oxygens, and that's good. In this picture, the negative charge, one of them is on phosphorus, and that's bad. So both of those things rule out this as being a good Lewis structure. It is still a legal or a Lewis structure that follows all of the correct rules, but it's not one that reflects nature. It is not one that the actual molecule really looks like, and so that's why we're discarding it. Okay. One last thing, and that is to notice that for all of these, even the bad one, let's assign the class. So here I have a central atom with 4 bonds. So this is AX4. No lone pairs on the central atom. Yes, there's a double bond. That is not a lone pair. So this is still AX4E0. What about here? AX4E0. What about this one? It's kind of hard to see now because I've done stuff to it, but again, 4 atoms around the central atom, AX4, and no lone pairs, AX4E0. So what this demonstrates is that when you do draw the Lewis formulas, it doesn't matter which of the resonance forms that you happen to draw. When you draw the Lewis formulas, it does not matter which one of these you happen to draw. They will give you the same information as what we had down here. The same shape, the same class, all the same characteristics that we're going to learn about how to deal with the Lewis formulas. They all give the same thing. Every single one of these, including even the resonance hybrid, by the way, gives the same formula. And so, the same class and the same steric number and the same shape, so forth and so on. So it doesn't matter which one of these you draw, you'll get the right answer to most questions. The only questions that you would get the wrong answer to by drawing an incorrect resonance form or a less good resonance form is particularly a question about formal charge. So for instance, if I gave you the phosphate anion and I said, what is the formal charge on phosphorus for the best resonance form of phosphate? Then you would have to say 0, and you would have to draw this one. This one has +1, but it's not as good as these two. This one has -1, but it's not as good as these two. These are the best ones, and they have 0 on the phosphorus. So the answer there would be 0. Other than that, if it's a question about class, if it's a question about shape or steric number, if it's a question about polarity, all of those are going to give you the same answer for any one of these pictures that you happen to draw. So the take-home message is don't worry too much about drawing the perfect Lewis formula. Just draw a Lewis formula that works correctly, that follows the rules, and you will get all the right answers for that unless the question happens to be specifically about resonance or formal charge. In that case, you need to be a little bit more careful, evaluate your formal charges, figure out which is the best resonance form, and go from there.